by looking at two more specific examples. So our goal for today is that we'll be able to solve for the centripetal force and acceleration in problems involving loop-the-loops and gravitrons. So loops, this could be anything from like a roller coaster, swinging an object in a circle, going on over a hill as you're driving, really anything where your circle is vertical rather than horizontal. And then we're also going to be looking at gravitrons. So these you might remember from like Swedish days or summer carnivals where you are basically in that big metal sphere and it spins around really fast and it makes you feel like you have zero gravity when your feet aren't on the ground. Okay, so it goes around so fast that you're able to be held up against the wall without falling. So our first example is going to be looking at a gravitron. Okay, so here we have our little friend, and we want to find the minimum coefficient of friction of that gravitron so that a rider does not slip on a gravitron with a radius of 5 meters and traveling at a velocity of 9 meters per second. Okay, so basically, how grippy does the material of that gravitron have to be so that a rider does not fall and hurt themselves? Okay. So whenever we're doing these, just like in last unit, always a good first step to draw our free body diagram. So looking at a rider here, we're going to have force of gravity pointing down. Okay? And here he's up against a wall. So that wall, our normal force, is going to be pushing perpendicularly and towards the center. Okay? And then since he would want to fall down if we weren't moving in circular motion, our force of friction is going to be pointing straight up here. And since we're trying to have our rider not slip and not move, this is going to be static friction. Okay. So looking at this, again, since our rider is not moving up or down, our goal is to have him stay still. That force of static friction up has to equal that force of gravity going down. So we know that in order to find our coefficient of friction, we're basically trying to find that force of friction. Okay. So our force of static friction, remember, can be anything up to that coefficient times our normal force. Okay. And we also know here that our force of friction pointing straight up has to equal that force of gravity pointing straight down, okay? Because we're balanced here. So since we have two equations for a coefficient of friction here, we can set these equal to one another. So we have our coefficient times our normal force equal to our force of gravity. So we know our force of gravity is always mass times point. They don't give us the mass of our rider here, so we're just going to leave that as a variable m. And then we know that's equal to our force of friction, which we'll find by doing our coefficient times that normal force. They don't give us any values for our normal force here, so it might look like we don't have enough information. However, if we look at our free body diagram, we can see that our normal force points inward. And we know whichever force points inwards towards the center of our circle, that is going to be equal to our centripetal force. Okay, so we know our normal force is equal to mass times velocity squared over r. Because again, that force pointing inward, that is always our net or our centripetal force. So that means if our normal force is equal to our centripetal force or mv squared over r, we can plug that in for our normal force in that force of friction equation. And when we do that, we can now see that we have mass on either side of our equation. If we have mass in every term in that equation, we can cancel those guys out. So that just leaves us with our coefficient times v squared over r is equal to 9.8. Okay, so our goal here is to solve for that coefficient. Okay? So we need to get that coefficient by itself. A good first step here would be to divide each side by v squared over r. And remember, dividing by a fraction is the same thing as multiplying by the reciprocal. Okay? So when we do that, we're left with our coefficient is equal to 9.8 times r over v squared. And then from here, we're given the values for our radius and velocity, so we're able to just plug those guys. So 9.8 times our radius of 5 meters divided by our velocity of 9 squared, and we'll find that we would need a minimum coefficient of friction of 0.605 in order for our riders not to fall. So if we use a material that only had a coefficient of, let's say, 0.4, that would not be great enough and our riders would fall. Okay. So we need at least a coefficient of friction or a surface that has a grippiness value of 0.065 at least so that our riders stay pushed up against the wall. Okay. What's important here is notice how our mass cancels. This is important when designing a carnival ride because you're going to have people of all different shapes and sizes riding that ride. So you want that mass to not affect how well they're able to stay pushed up against the wall. Okay, so here, riders of any size could ride this ride without falling. Okay. Something else to kind of notice here that might be helpful is that if our velocity was greater, okay, there we would be dividing by a larger number, so our coefficient could be smaller. Okay, so since we're dividing by that velocity, if we were traveling faster, we would end up with a smaller coefficient of friction and our surface could be less grippy. Problem where our normal force is equal to that centripetal force, we're going to look at a loop-the-loop problem. So here we want to find where is the normal force the greatest. And something that's really going to come in handy here is finding our centripetal force. So remember, our centripetal force is always equal to mv squared over r. So what's kind of important to note here is as we're going around the circle, our mass is going to stay constant. The radius, since it's a circle, is also going to be constant. And since we're moving at a constant velocity, our velocity will also be constant. Okay? So our centripetal force as we move around a loop-to-loop does not change. Because all the variables that we use to calculate that net force, that centripetal force, are going to remain the same. So that's going to come in handy as we're looking at these 3 different points on our loop. So if we look at point A, here we're at the bottom of the loop. Okay? At the bottom of the loop for a free body diagram, remember, free body diagram is always your first step. We'll have our force of gravity pointing down, and here the track is pushing up on us. So our normal force is pointing upwards. And remember, our acceleration always points towards the center of our circle. So here, our normal force is going to be is going to be greater than that force of gravity. When we're moving in a circle, acceleration always points towards the center. So here, our force pointing towards the center is going to be greater. So if we want to find our centripetal force, what we're going to do is we are going to take our force pointing towards the center, that normal force, and we are going to subtract the force pointing in the opposite direction. Okay, so it's handy to make the force pointing towards the center. That's always going to be kind of our positive force because that's the direction our acceleration is pointing. And then the force pointing opposite that center, we're going to subtract that one. So in this case, our force of gravity. So if we want to compare our normal force, here, to solve for our normal force, it'd be our centripetal force plus our force of gravity is equal to that normal force. Okay? If we look at point B, here our free body diagram, our normal force is going to be pointing towards the center. Okay? Because that wall is on the right-hand side, so it can be pushing that cart towards the center of our circle, and then force of gravity goes down. Since our centripetal force always points towards the center of our circle, and we only have one force pointing towards the center here, it's our centripetal force that's equal to our normal force. And then last but not least, for our motion at C at the top of the track here, we're going to have two forces pointing down. Because here we still have our force of gravity pointing down. But since the track is kind of above that cart now, that track itself is going to be exerting a force down on that cart. So here our normal force also points down. So since we have two forces pointing down or towards the center of our circle, here our centripetal force will be equal to our force of gravity plus that normal force, since both forces are pointing in the direction of that centripetal force or in the direction of our acceleration. So here, if we wanted to solve for our normal force, it'd be our centripetal force minus our force of gravity is equal to that normal force. Okay, so if we look, we have three different situations of our cart, and we have three different equations for that normal force depending where we are. We said our centripetal force does not change. Also, our force of gravity as we go around, that's just mass times 9.8. Force of gravity is also going to remain constant. Okay, so our Fc and our force of gravity remain constant. So that means it's our normal force that changes as we go around. Okay? So if we want to compare our normal force at these three moments, okay, we can see that at point A, we have to add our centripetal force and our force of gravity to equal that normal force. So here, since we're adding those two forces to equal that normal force, this is going to be where our normal force is. Okay? Whereas if we look at point C, here we're doing our centripetal force minus that force of gravity. Okay? So if we compare situations B and C, B, that centripetal force, is equal to our normal force. But in C, our centripetal force minus the force of gravity is equal to that normal force. So here, since we're subtracting those two values, this is going to be where our normal force is the least, which makes sense, right? You don't want a large force pushing down on you when you're on top of the track, right? You want to make that force as small as possible. Okay. So looking at this, since our centripetal force and our force of gravity remain constant, it's just that normal force that is changing. Okay. And at the bottom, since we have to add those two forces to equal our normal force, that is where our normal force will be the greatest. Whereas C, we're subtracting our centripetal force and our force of gravity. So that would be where our normal force is the least. What is kind of also important to note here, if you're trying to find the minimum velocity to make it around that track without falling down. Okay. So you're trying to find as slow as you can possibly go without falling. You are going to want to look at the top of the track because the top is going to be where you're most nervous. Okay? And if you're trying to find as slow as you can possibly go, if we look at our free body diagram, your force of gravity, that's not going to change. That is constant. It's your normal force that we can change. So if we want a small value, we're going to assume at the top, our normal force is equal to 0. So that means when we're trying to find the minimum velocity to make it around the track without falling at the top, we would only have that force of gravity equal to our centripetal force. Okay? Because we're just going to get rid of that normal force altogether. Okay, we're just barely touching the track at that point. So we'd only have that force of gravity pointing towards the center. Okay? So again, some big ideas there. Centripetal force always points towards the center of the circle. And we're always going to make the force pointing towards the center positive, whereas the force pointing away from the center is going to be negative. I'm going to look at one more example where we are moving in a vertical circle. So kind of like our loop problems, but here we are going to be swinging a 0.8 kilogram ball on a string in a vertical circle. Okay, So we want to draw and label force diagrams to show all forces acting on the ball at the top and bottom of our sphere. Okay, so when our ball is at the top, okay, here, okay, we have our string. We're going to have that force of tension from the string pointing down, but we're also going to have our force of gravity. Okay, because force of gravity always points downwards, but since we also have that string kind of pulling us down, we're going to have that force of tension pointing down as well. Okay, whereas at the bottom, here, our string would be pulling us up towards the center. So we'd have that force of tension pointing up. And since the force of tension is pointing towards the center of the circle, that is going to be the direction of our acceleration or the direction of our largest force. And then we'll have that force of gravity pointing down. Okay. So if we want to find the tension in the string at the top of the circle, the ball has a period of 0.2 seconds. Okay. So at the top of the circle, we said we have two forces pointing down. So to find our centripetal force, since we have two forces pointing towards the center, we want to add our force of tension plus our force of gravity. So just like in last unit, once you have your free body diagram drawn, write your net force or your centripetal force equation. Okay. So in order to plug in numbers, I need to find what my centripetal force is. Okay. So remember, centripetal force is mass times velocity squared over r, and that'll be equal to my force of tension plus my force of gravity, which I know is mass times 7.8. Oh my goodness, my pen is being a stinker. There you go. Okay. So if we look at this problem, it tells us our mass is 0.8, and it tells us our radius is 1. However, it does not just directly give us our velocity. However, we do know we have a period of 0.2 seconds. And we know for velocity, it's how far we travel over how long. So for a circle, how far we travel is going to be our circumference because we're moving in that circular path. So we would do 2 pi r divided by how long it takes to move around that circle once. Our period, that's going to be the time for one revolution. Or the travel the distance, 2 pi r. Okay? So we'll do our circumference, 2 pi r divided by that period. So when we plug in values, we know our radius is 1. And it's going to be the same as the length of our string because the length of the string will go from the center of the circle to the bottom. And then times or divided by a period of 0.2. Okay? So this tells us we're moving with a constant velocity, 31.42. Okay. So now that we know our velocity, we're able to plug this into our net force equation. So we know from our problem, our mass is 0.8. We know our velocity now is 31.42 meters per second, squared, divided by a radius of 1. Okay? And that'll be equal to our force of tension plus our force of gravity. So our mass is 8 times. Okay? So if we want to get our force of tension, we just have to subtract our force of gravity from either side. And we should get a force of tension of 781.73. Like we are kind of talking about in the previous problem, if we wanted to find the minimum velocity the ball could travel in that circle, we would assume our force of tension at the top was 0, and therefore our force of gravity would just be equal to that centripetal force. Okay, so if we wanted to find the minimum velocity that the ball could go around at, we would assume that the force of tension going down was 0, and then our centripetal force would just be equal to our force of gravity. Okay, so then looking at C, here we want to find the force of tension at the bottom of the circle. So here, when we write our net force equation, our force of tension points towards the center. Okay, so it's going to be a positive value. And the force of gravity points the opposite way. Okay. So if we want to find our force of tension, we're going to want to do our centripetal force plus that force of gravity to equal that force of tension. So we can kind of see here that our force of tension at the bottom, again, is going to be greater, okay, because we need to make up for that force of gravity pointing in the opposite direction. Okay, so if we look, we already found our centripetal force in that previous problem. We said our centripetal force is 0.8 times our velocity of 31.42 squared over our radius of 1. So again, that centripetal force is not going to change throughout our circle because we're moving at a constant velocity. And then we just need to add our mass of 0.8 times 9.8 to get our force of gravity. And when we add those together, we'll get our force of tension. And we'll see at the bottom of the circle, our strain has a force of tension of 797.61 newtons. Okay. And that makes sense because we said our force of tension at the bottom is going to have to be greater to make up for the force of gravity pointing the other way. Okay. So when you're doing these problems, same process as before. Always show your free body diagrams first, and then whatever forces are pointing in the plane that is in the direction of the center of the circle, you'll use those to find your centripetal force. So you always want to see what forces are pointing towards the center of that circle or pointing directly opposite to see which forces you'll have to add and subtract. Okay. If you guys have any questions, please let me know. Otherwise, I hope you guys have a great day.